Please note that in the YouTube description we have links to Discord, Patreon, and the sources that I referenced to be able to make this video. Pierre-Simon Laplace was a 17th and 18th century French polymath. His work was highly influential in engineering, mathematics, physics, and philosophy. Some notable contributions amongst his massive body of work include the Bayesian interpretation of probability, the dynamic theory of tides, the Laplace transform, and Mécanique Céleste, a revolutionary physics work that defined classical mechanics through calculus. Laplace was born on March 23, 1749, in Beaumont-en-Auge, in Normandy. His parents were Pierre du Laplace, who worked in the cider trade, as well as being involved in real estate, and Marianne Sauchon, who came from a very wealthy farming family that owned land in Trousgeville, Normandy. The Laplace family was involved in agriculture until 1750, and then Father Laplace got more serious about cider trading. At age 7, Laplace began attending a Benedictine priory school in Beaumont-en-Auge, and when Laplace was 16, he began attending the University of Caen, majoring in theology as his father wished for him to pursue religion. While there, he quickly gained an interest in mathematics, being mentored by mathematicians Christophe Godbled and Pierre-Luc Canu. Alas, there's really no information on these mathematicians other than their recognition of Laplace's abilities and mentorship. After his second year at the University of Caen, Laplace realized he was far more interested in pursuing mathematics than he was in pursuing the Roman Catholic Church. So he left Caen to go to Paris, with a recommendation letter from Luc Canu for Laplace to present to Jean-Laurent d'Alembert, an 18th century French polymath most notable for his formula for obtaining solutions to the wave equation, as well as providing the earliest attempted proof of the fundamental theorem of algebra. D'Alembert was working as a researcher at the French Academy of Sciences at the time, and it didn't take much for him to recognize Laplace's abilities. He took Laplace under his wing, and after working together for a bit, D'Alembert recommended Laplace for a lecture position at École Militaire, a role which ended up giving a lot of exposure to those who were in powerful positions, or eventually took powerful positions in France. A good example of this is that Laplace had Napoleon Bonaparte as a student in 1784. The lecture position at École Militaire wasn't very demanding and provided Laplace with a stable income, so he was able to really throw himself into research. He first presented his work to the French Academy of Sciences in March of 1770, discussing a work on the extrema of curves, which improved on work from Joseph-Louis Lagrange, an Italian-born French mathematician and astronomer, primarily during the 18th century, most notable for developing Lagrangian mechanics. After Laplace translated the work into Latin, it was published in Nova Acta Eruditorum in 1774. The next paper he presented was in July of 1770, presenting a work on difference equations, and in 1771, Laplace published a few papers. One paper was on integral calculus and was published in Nova Acta Eruditorum. Apparently it was riddled with errors due to the printer, so when republishing it 6 years later, Laplace prefaced the paper with an apology. Another paper he published was a work he'd started while in Caen, titled Research on the Calculus of Infinitely Small Differences and Finite Difference. The work was published in Mélanges de Turin, and it provided the first exchange between Laplace and Lagrange. Now, by 1771, Laplace really wanted to get into the French Academy, felt entitled even, but he was passed on until April of 1773. At which point, he was elected an associate member of the Academy. By the time he was elected, Laplace had already presented 13 papers, including work on the invariability of planetary orbits, so it was really just a matter of time before he was admitted. For much of Laplace's career, he was very invested in mathematical physics, so we'll give a glimpse into some of his developments. In 1775, Laplace developed the dynamic theory of tides, which describes the ocean's real reaction to tidal forces. The theory takes into account friction, resonance, and the natural periods of ocean basins, and explains why tides can be up to 15 meters. The equilibrium theory, founded by Newton, only calculates height up to half a meter or less, and since the equilibrium theory ignored the Earth's rotation, it was unable to explain real ocean tides. Measurements have confirmed the theory, providing possible explanations for many things, including how tides interact with deep-sea ridges. With the help of satellites to confirm accuracy, tides worldwide are now measured to within a few centimeters. That same year, Laplace published a memoir on the stability of the solar system, focusing on Jupiter's shrinking orbit and Saturn's expanding orbit. Euler and Lagrange had previously worked on the problem, ignoring the small terms in their approximation, but Laplace noted their necessity, that when they're integrated over time, they could prove important. He expanded his analysis to higher order terms and came to the conclusion that any two planets and the Sun must be in mutual equilibrium. During the early 1780s, Laplace began doing research with Antoine Lavoisier, an 18th century nobleman and chemist considered to be the father of modern chemistry. In 1783, they published a paper on their findings from researching heat, titled Memoir on Heat, discussing the kinetic theory of molecular motion and the experiments they performed, which included the measurements of the specific heat of various bodies, the measurements of metal expansion under increasing temperatures, and the measurements of ethanol and ether's boiling points under pressure. Amongst their findings, they showed that the speed of sound in air depends on the heat capacity ratio, or Laplace's coefficient, which is the ratio of the heat capacity at a constant pressure to the heat capacity at a constant volume, and that respiration is a form of combustion. Again in 1783, Laplace published a paper, this time developing the idea of scalar potential, which is the situation where the difference in the potential energies of an object in two different positions is independent of the path taken to get from one position to the other. Work had already been done on potential over the years by the likes of Daniel Bernoulli in his work Hydrodynamica, Euler, and Lagrange, who had developed this theory in the 1770s, publishing it in full in Mécanique analytique. Laplace applied calculus to the potential function, yielding what would be coined as Laplace's equation, which is given as the sum of second derivatives of a twice differentiable three-variable function, summing up to zero. This equation is proven pivotal, being used in fluid dynamics, electricity and magnetism, and Laplace's subsequent work on gravitational attraction. In 1785, Laplace was promoted to a senior position at the Academy and also published a work expanding on work done by Euler a few years earlier, developing what became known as the Laplace transform, which is an integral transform method that can substantially ease finding the solution to a linear ordinary differential equation. Euler initially only looked at solving differential equations of the form z equal to the integral of f of x e to the ax dx, and z equal to the integral of f of x to the a dx, whereas Laplace took the key step of using integrals of that form to transform entire ordinary differential equations. From a physical standpoint, he converted a function of time to a lower order function of space, and upon solving for the transformed equation, the solution is inverted to obtain the actual solution to the original equation. The method has proven itself fundamental in many areas today, including electrical engineering, signal processing, and optics. On March 15, 1788, at age 39, Laplace married 18-year-old Marie-Charlotte du Château de Romanche, who was from a wealthy family in Besançon. Their wedding was in Saint-Sulpice, Paris, and the pair had two children together, Charles-Émile and Sophie Suzon. In May of 1790, Laplace was made a member of the committee which was to standardize weights and measures, working on the metric system and advocating for a decimal base. He worked alongside scientists like Lavoisier and Lagrange, who had arrived from Berlin just a few years earlier. Come 1793, the Reign of Terror began and everything but the research and the standardization committee became inhibited at the Academy. Basically everyone except Lagrange was thrown out of the committee because of their views. Note that this was not Lagrange's decision, this was just the nature of the beast that the Reign of Terror brought on. While Lavoisier and other scientists were executed, Laplace was lucky enough to escape such a fate. In fact, him and his family had moved 50 kilometers southeast of Paris just before the Reign of Terror began, avoiding much of the chaos that ensued, not returning to Paris until July of 1794. In 1795, Laplace lectured briefly at the university called École Normale, a school funded with the goal of training school teachers. The issue that presented itself was that most of the students couldn't comprehend the majority of the information they were being taught by any lecturer at the university, so it ended up closing after only 4 months. Laplace was able to teach a few courses during its short time, which included probability theory. Laplace actually ended up publishing a paper based on these lectures in 1814, which we'll discuss later on. This same year, the French Academy opened back up, and the Bureau des Longitudes was founded, with Lagrange and Laplace amongst its founding members. Laplace went on to lead the Bureau, as well as the Paris Observatory, and he was criticized for being too theoretical while leading both. In 1796, Laplace published Exposition du Système du Monde, which provides a survey of the solar system, giving general explanation of phenomena without detail, as well as giving a brief history of astronomy. The final part of this work, Laplace also presents the nebular hypothesis, which suggests that the solar system is formed from gas and dust orbiting the sun. The theory was originally outlined by Immanuel Kant in 1755, but Laplace didn't credit him, so it's not entirely known whether Laplace even knew of Kant's work on this. A few years later, in 1799, Laplace published his strongest astronomical work, Mécanique Céleste, which covers much of the detailed exposition left out, and then some. The ultimate goal of the work was to essentially translate Newton's Principia Mathematica into the language of differential calculus, as well as fill in details Newton wasn't able to fill in himself. It consisted of 5 volumes, the first 2 volumes both being published in 1799, containing methods for calculating motions of the planets, determining their figures, and resolving tidal problems. The third and fourth volumes were published in 1802 and 1805 respectively, containing applications to the subject matter addressed in the first 2 volumes, as well as containing several astronomical tables. The final volume was published in 1825, and it was mainly a historical overview. It also contained appendices of the results from Laplace's research at the time. It must be noted that much of the findings were actually from other people. This is unlike the Kant situation. Laplace just didn't want to give credit. This was obviously not very cool of him, but it was a common problem at the time, and many scientists partook in this activity. In November of 1799, Napoleon executed a coup and came to power in France about a month and a half later. He appointed Laplace to be the Minister of the Interior. Alas, Laplace only lasted until Napoleon gained full power, and then the role was assigned to his brother, Lucien Bonaparte. Apparently, Laplace's performance was lackluster, with Napoleon expressing Laplace was too mathematical, bringing on more problems than not. But it's more than likely Laplace was always going to be temporary, just there as a placeholder until full power was achieved. Despite this, Laplace was still fairly involved in politics, much to the dismay of his colleagues, who were now viewing Laplace as an opportunist. Sadly, over the years, Laplace lost many relationships due to politics. The relationship between Napoleon and Laplace was quite strong for a few years, discussing matters ranging from basic philosophy or politics to religion. There was a rather infamous interaction between them concerning the existence of God in August of 1802. With Napoleon commenting that Mécanique Céleste makes no mention of God. Laplace's response was claimed to be, "I have no need of that hypothesis," and this was circulated around for many years. This comment was important to people because it made Laplace seem like an atheist in a Catholic-dominated time. Laplace was raised Catholic and was actually more of an agnostic in his final years. The apparent real account of the exchange was noted by Sir William Herschel, an 18th and 19th century German-born British astronomer and music composer, notable for constructing the first large telescope. Herschel was there for the exchange and stated that Laplace wished to show that a chain of natural causes would account for the construction and preservation of the wonderful system. So despite any religious views Laplace had, he wanted to leave religion out of science. In the early 1810s, Napoleon and Laplace's relationship began to rapidly dwindle. At first, it was because Laplace had lost respect for Napoleon, with Laplace feeling Napoleon was a pretty lousy leader who wasn't living up to his word. But what really broke the camel's back was when Laplace's daughter died while giving birth in September of 1813. Though happy that his granddaughter survived, Laplace was obviously pretty upset about losing his daughter, and it showed when he went into work. Napoleon was incredibly insensitive about this matter, whereupon hearing this news, he stated, "You are a mathematician. Put this event in an equation, and you will find that it adds up to 0. It's not too surprising to find that Laplace vehemently supported the return to power of the Bourbon dynasty from 1814 to 1815, as it directly opposed Napoleon. In 1812, Laplace published a work on probability theory, split into 2 books, titled Analytical Theory of Probabilities. The first book included generating functions, which Laplace had actually addressed in a 1779 paper, and approximations to various expressions, such as approximating the binomial theorem to the normal distribution, which is coined as the de Moivre Laplace theorem. The second book included Laplace's definition of probability, Bayes' rule, which was given that name by Poincaré years later, the method of least squares, and applications to life expectancy and marriage length. In 1814, Laplace wrote a paper titled Philosophical Essay on Probabilities, which ended up being a part of Analytical Theory of Probabilities from the second edition onwards. His aim of the paper was to create a mathematical system of inductive reasoning based on probabilities. He began the text listing out his principles for this system, with one of the principles being the extended form of Bayes' rule, and another principle being the well-known rule of succession, which states, suppose we repeat an experiment that we know can result in a success or failure, and we do so n times independently. If we have s successes, then the probability the next repetition is a success is s plus 1 divided by n plus 2. The example Laplace gave to present this was the probability of the sun rising tomorrow, given that it had never failed previously, and it initially gave the rule a bad rep, being deemed as absurd by many readers upon seeing the solution. Later editions of the Analytical Theory of Probabilities, besides including work from his philosophical essay, addressed errors in observations, discussed triangulation methods in surveying, and further developed generating functions. For his remaining years, Laplace continued to work on physics and mathematics, albeit with less influence than he'd had prior. On the morning of March 5, 1827, Laplace died in Paris, with the cause of death probably due to natural causes. Typically, it was hard to get the Academy to cancel any kind of event or meeting, but Laplace's death basically caused a shutdown as a sign of respect. And it took the Academy over a year to fill the role Laplace's death left open, with the first 6 months of that being a time where they just didn't even want to fill it. Laplace was buried at the Père-Lachaise cemetery, and was survived at the time by his wife, his son, and his granddaughter. Well, there you have it. A brief history of yet another mathematical great. We'll end on a quote from Laplace on his philosophy towards science. If man were restricted to collecting facts, the sciences were only a sterile nomenclature and he would never have known the great laws of nature. It is in comparing the phenomena with each other and seeking to grasp their relationships that he's led to discover these laws. If you enjoyed the video, please click that like button and subscribe. And if you generally just enjoy the content of this channel, please consider supporting on Patreon. As always, thank you for watching, and I'll catch you next time.
Alright. I had to watch this one because in the random math, physics, science stuff I read, I get confused. I see Lagrange, I see Laplace, and I don't know who's who. But now I have a basic understanding of the person, the human named Laplace, and I also saw the video for Lagrange, so now I should be able to just know those two apart. Man, I just love this series, these biographies of these great scientists are just really, it's really easy to follow. It's not like a lot of math, it's like, it's so difficult to follow. But yeah, just following a life is really good. I really like this guy's YouTube channel. I wish there were more like this, but there's not that many YouTubers doing biographies of scientists. Anyway, that's all that I have to say right now for this one.